Hi, this is Roger from Labs today with the fourth episode about precision op-amp design with the example of our total harmonic distortion meter. And today we'll concentrate here on the combination of the chain of three op-amps here in the lower branch. Just to recap, we have already extensively spoken about the first op-amp, which is only a unity gain buffer, so we don't expect any more problems from this one here. But then comes an attenuator with a potentiometer, and behind that another same op-amp, an NE5534, with an amplification of around 8. And from there on, the circuit branches off either to the, or both, to the notch filter, our 1 kHz Wien-Robinson filter, just to make the distortion measurement. And here on the lower branch to another op-amp in an inverting configuration, which not amplifies but attenuates by a factor of 5, or you can see it as times 0.2. And the reason why we have this strange configuration is the lower branch, just to set the 100% reference level, has to give 1/10 of the amplitude compared to the output of the Wien-Robinson bridge, because in the upper position of the switch, our measurement circuitry and our ADC is has 10 times the resolution. So that's why here we first amplify and then attenuate again, and we will see that this configuration is perhaps not optimum. So we have to remember just two things. Here at this point, the full scale 100% level is equal to an amplitude of 800 millivolts peak, which on the other side, of course, means when this amplifier attenuates by a factor of 5, that here we have 4000 millivolts peak, or 4 volts peak. We will later see, when we discuss in another future episode the workings of the Wien-Robinson notch filter and the 50 Hz filter, etc., that the choice of 4 volts peak at this point is quite okay. So we have to have this amplitude here compared to our reference level of our 1 kHz fundamental tone must be 4 volts peak here. But we will discuss if this configuration of, we have the input attenuator, then a buffer, another resistor attenuator, an amplifier, an attenuating amplifier, if this is really the optimum. And before that, we will just take a closer look here at this chain of op-amps, just to find out some details. And we will make live distortion measurements and frequency response measurements, and then talk a little bit also about the noise, at which stage of these three it becomes important to look at resistor or op-amp noise. So first of all, let's look at a clean picture of how the chain of these three op-amp is looking. We will discuss this just in a minute in detail, but beforehand, if you haven't seen it already before, you might wonder, well, what are these 4 capacitors for? We have 2 here connected directly to the NE5534, and then here at the outputs we also have 100 picofarad capacitors directly going to ground. Now that's quite unusual, because one of the rules is you should never connect a capacitive load directly to the output of an op-amp. This could give you ringing and oscillation and all kinds of unwanted behavior. So Very strange, and so I still haven't found out what is the purpose of them. Perhaps you have a guess. I have something in mind why they did it, but you can see these two lower 100 picofarad capacitors at the output of the op-amps, they are in parallel with a resistor, so they kind of bridge the resistor at higher frequencies, but this only becomes important at frequency above 100 kilohertz. And a very strange combination, and I can't remember to have seen such a configuration, but perhaps it has to do something with these so-called compensating capacitors. And therefore we'll take a step back and look again in the datasheet of the NE5534, and what can quickly be overlooked is this here, directly at the descriptions. The op-amps are internally compensated for gain equal to or higher than 3. The frequency response can be optimized with an external compensation capacitor for various applications, for example a unity gain amplifier or high capacitive load, etc. etc. So let's take a look back again. Here, our first op-amp. This is a unity gain amplifier, and we just saw, so it is designed for gains equal to or higher than 3. Well, our second op-amp here, this one satisfies this rule because here the amplification by the means of the two resistors in the feedback loop is 7.9. So here the gain is greater than 3, but here we have a gain of 1. And there is another trap. Look here in the app note. There are companion chips to the NE5534. There's also a 5532 and a 5533. And this app note is for all three of them. And now read closely. The op-amp is internally compensated for gains equal to 1. But this relates only to the first two ones, the NE5532 and 33. So be very careful. Also, datasheets and app notes contain errors. So if we now took a closer look at the diagrams in the datasheet of the NE5534 we've used here, we can see directly at the beginning some graphs that are of interest of us. First of all, the open loop frequency response, once without any compensating capacitor with 0 picofarad, and then you can see with 22 picofarad here the open loop frequency response is slightly lower. Most interesting is this here, slew rate as a function of compensating capacitance. So at the circuit they are using 100 picofarad, and you can see the slew rate goes down from about 14 volts per microsecond down to around 2 volts per microsecond. Now this is exactly to the effect to make even an or only partially compensated op-amp capable of working at a gain of 1 by lowering its slew rate and lowering its open loop frequency response. And here you can see probably even 22 picofarad would have been enough, because here the lower curve is for a gain of 0 dB, which means a gain of 1. And so this thing is stable as a unity gain amplifier or buffer if you use at least 22 picofarad. And the higher you choose your compensating capacitor, the more stable this gets. We can see another graph here, the large signal frequency response. You can see it also goes down the higher the compensating capacitor becomes. Now we won't discuss stability of op-amps here, because whenever possible you should use a unity gain stable amplifier. This is directly stated at the first page of every datasheet. If the op-amp is designed for gains greater than 3 or 5, or if it is unity gain stable without any further compensation measures, like a compensating capacitor. The most famous example is perhaps one of the earliest high precision op-amps, the OP27 and its companion, the OP134-series. They were extensively used also in high-end audio equipment, starting from when they appeared, probably from the late 70s or early 80s, and the OP27 is unity gain stable, and the 37, its companion, is uncompensating, so it has a higher frequency response, but it is not stable at a gain of 1. And we will talk about that again in another episode when it comes to the difference between inverting and non-inverting amplifiers, etc. Let it suffice for now that probably the reason why, at least here, they choose a relatively high value of 100 picofarad is to make these op-amps 100% stable and somehow to limit the frequency response, so that also noise in the region above 1 megahertz is suppressed at the output, simply because the frequency response doesn't get any higher than a few hundred kilohertz. But I still don't know what here the lower ones are for. Do they add stability? Now let's just make an experiment. The easiest way to check is you just put a square wave at the input and take a look at if the output, if there is any ringing or any instability, and we'll make this experiment just now. So let's take a look what happens to a square wave in our op-amp chain. This is the input signal. You can see there's a little changing kind of ringing here. That is certainly comes from the analog to digital converter in the external audio sound interface that I'm using here. So this is not present in the original signal coming from my signal generator. Anyway, we have basically a clear 1 kilohertz sine wave, and let's take a look how it looks behind the first unity gain op-amp. Except for the attenuation by a factor of 2, the signal is unchanged, still looks clean, although if we increase the amplification a little bit, you can see now there's a little slope here. That comes from the limitation of the input capacitor, which cuts off DC voltage, and you can see this basically is here a DC voltage for half of a millisecond, and so this has nothing to do with the op-amp, but simply with the AC coupling of the input capacitor. So signal is clean. Now let's go behind the second op-amp, and that is here. We have to change the y-axis a little bit, and signal still is clean. So the compensation obviously works okay, and just to be sure, we still take the third op-amp, the attenuating TL081. Again, let's change the amplification a bit. So in all three op-amp stages, a square wave comes out unaltered and clean. So everything all right. And now let's measure the frequency. We already can see now if the signal comes out with sharp edges, the frequency response will be probably even higher than 20 kilohertz, but let's just check it and measure up to 40 kilohertz. So apparently the square wave gives quite a good result. We have no distortion, no oscillation, no ringing introduced by none of the three op-amps, so that is quite okay. We could go to the effort just to desolder here the 200 picofarad capacitors and see if the output changes from our square wave, but I don't want to at the moment. So next is let's check the frequency response. If the frequency response is linear in the important region from 1 to 20 kilohertz, and if we can observe any fall off, perhaps at 40 kilohertz or somewhere else. So let's measure the frequency response from 1 kilohertz to 40 kilohertz and see if there is any fall off at the higher frequencies. Because I know that my sound card has a slight fall off above 20 kilohertz, let's first measure simply the output of the sound card as a reference, and then we'll go to the output of the OpAmp stage. So this little dip was of no importance. That was because I didn't held the tip here, the probe, not very tight. So next is, let's go to the output of the third OpAmp and measure again. And we can see it's flat until now. And you can see above in the green curve the very slight fall off above 30 kilohertz. And we have exactly the same frequency response here. So there's no limitation in frequency response from the three OpAmps. So here we are back at the circuit diagram of the input stage, the sequence of three OpAmp. I've removed the capacitors so that they just don't disturb us anymore. So we already know the first stage here is just a unity gain input buffer. Now here comes an attenuator, and let's just for a moment think about what happens if the potentiometer is at the upper position, and what happens if it's at the lower position. Now when it's at the upper position, the center tap is directly connected to the output of the first OpAmp, so we have no attenuation at all, and that is where we get the 0 dB amplification or attenuation. When it is at the lower point, then we have a voltage divider of 10 kilo ohms, and here these two resistors in parallel, 820 and 1.5K, which gives something around 500 and something ohms. And that means an attenuation of 20, or in other words, times 0.05, or if you calculate in dB, this is an attenuation of minus 26 dBs. Now, just to recap, we need this variable attenuation simply because we have different input signals ranging from, I think, what was it, 40 volts peak, which could come from an output amplifier, or at the minimum, I think 250 millivolts RMS. And these must be brought up to a reference level, as we have seen, to 4 volts peak at this point. And therefore, we need, of course, a kind of tuning, a kind of variable, either variable amplifier or, in this case, a variable attenuator. But if we attenuate, then we have to re-amplify, and that is the purpose of the second OpAmp. And this is, of course, the critical one, because it amplifies, if you do the math, by a factor of 7.9, because here we have two resistors in the feedback loop. It's in the non-inverting configuration. So 6.8K at the lower end, 47K at the higher end, and if you do the math for this voltage divider, it's just a factor of 7.9. So let's round this up to times 8. And now you can look upon it at this way. All or most of the error terms that exist in an op-amp are at the output just simply amplified by the gain or amplification factor. So because our first op-amp has a gain of 1, we don't expect here any problems. If there were, then the problems here at the output of the second op-amp would be 8 times larger. Today we won't discuss the DC errors like DC offset and input bias, etc. That will be the topic of another episode, because we are here only measuring AC voltages or AC currents, depending on how you look upon it. DC errors are at the moment of no interest, because we can simply at the end filter them out with a blocking capacitor. But what about the AC errors? And the two most important here in our circuits are, of course, total harmonic distortion. We don't want that this amplifier here introduces any total harmonic distortion. And the second is noise. Now, before we go to measure the effect of the total harmonic distortion, let's just talk for a minute about the noise. We already started this theme or topic in the last episode, but now here it could become really important. And let's take a look at the worst case that could happen. So this is the simplified schematic of this block. The worst case could be here our 10K resistor. If our 10K pot is at the lower position, giving this voltage divider with the two parallel resistors which give 530 ohms. Now the first question is, does resistor noise come into play here? Well, I myself, as you remember, have fallen into the trap. If this 530 ohm resistor would not exist, then we would have to consider the noise from the 10K resistor. But the 10K resistor, because here the output of our unity gain buffer is a low impedance source, this kind of goes to ground. I know it's a little bit difficult to understand, but in this configuration concerning the noise, the 10K resistor noise is like it is in parallel with the 530 ohms, and so it simply doesn't come into play. Our limiting factor would be the 530 ohm resistor when we look at as these two in parallel. And we can already now say absolutely safely the resistor noise from a 530 ohm resistor will give no problem at all for our circuit. So we don't have to calculate it, you just know this. When you once did the calculation, you know that such low resistors don't give any problems at the levels we are speaking here. Now, but what about our 8 times multiplying op-amp? Now, from the data sheet, we know that the noise that the NE534 itself gives is 4 nanovolts per square root of the bandwidth. And now we said we want to limit our bandwidth to 20 kilohertz. Let's say our op-amp stages all go to 100 kilohertz. So we take as the bandwidth 100 kilohertz, so really worst case. And then if we multiply this, so 100k, the square root of this, times 4 nanovolt gives us 1.26 microvolts. Oh, let's round it up to 1.3 microvolts. Now, and there comes now a very important concept or trap again. When you have multiple stages, you always have to know, well, to which point is this related? Is it related to the input or to the output of the op-amp? And this 1.3 microvolt is present here at the input related. This is the input related value. But because this op-amp multiplies by, rounded to, a factor of 8, if we consider it or set it in relation to any voltages at the output, we of course have to multiply this with the gain of our op-amp, because here at the output the 1.3 microvolt at the input are of course multiplied by a factor of, let's do it exactly, 7.9, which gives us, rounded nearly exactly, 10 microvolts. So our noise voltage, which is sometimes noted as En, and we could have another point RTO, that means related to output in comparison to ENRTI related to input, is 10 microvolts. So this is simply the noise generated by the op-amp itself. And now we know, and this is of course RMS. Noise is usually given in RMS, because you can't give any peak values for noise due to its statistical behavior. So now, if we remember our specifications for our circuit, we had to have all harmonics and all noise smaller than 90 dB, or at least 90 dB below our reference voltage. Now, let's see how many dBs this is below the 1.41 volts that we have here as the reference point. 1.4 volts RMS in relation to 10 microvolts gives us a factor of 141,000, or rounded 140,000. Now what is that in dB? So take the logarithm times 20, and that means 102.99 dB, or 103 dB. So this is what is also called the signal to noise ratio. Our signal is 1.41 volts RMS reference voltage. Oops, again, sorry, now you can see it. Our noise is 10 microvolts RMS, given by the characteristics of the op-amp and the gain factor. And the difference is a factor, or the ratio is a factor of 140,000, and translated to dB, this is 103 dB, so it's 13 dB better than what we want it to be, so we can be sure noise from this op-amp, even though it amplifies by a factor of 8, does not give any problems here. But if you design stages that have to be exact and noise-free for 100 dB or larger, then this op-amp, even though it's a low, it is a low noise op-amp, but it wouldn't be sufficient here. So we can safely say noise does not play any problem in our whole circuitry. Not in the input amp, because this one only amplifies by a factor of 1, and because this is the only really amplifying stage here, it won't play any role in the further stages, because simply the signal to noise ratio here and the signal itself is so high that noise, simply you know that from experience, it won't play any problems, or it won't give you any problems from here on. So what remains is the total harmonic distortion. And therefore we first of all take a look back again at the datasheet. So strangely, you do not find this in the datasheet from NXP, but only in the one from TI. So that's one of the reasons why you should, with parts that are available from different manufacturers, you should download old datasheets. And here we see the total harmonic distortion versus frequency. And the only point of interest is here at 1 kilohertz we have 0.002%. This is slightly better than what we need. We need no more than 0.003%, so that is okay. But you have to be very careful. Look, the test conditions at a gain of 1 and at a supply voltage of plus minus 15 volts. Now we are having plus minus 12 volts, so this is quite near to plus minus 12 volts. But remember, our second stage has a gain of 7.9, and we don't know what happens when we have a gain of 8. Does the total harmonic distortion remain at 0.002%, or is it raised by the gain of the op-amp? Let's just measure the two stages. The first one does have, as we know, as a unity gain buffer, does have a gain of 1, but the second one, that will be interesting. So let's go and measure. So first of all, let's measure the output of our Wien bridge oscillator. You can see the relative sharp spectral line here, and you see no harmonics, no second, third, etc. up to 20 kilohertz, up to the span of minus 100 dB. So this thing is better than 0.001% in producing no harmonics. What you see is these little spectral lines here. Also this peak here, these are multiples of 50 Hertz noise, so they have nothing to do with our 1 kilohertz signal. Nevertheless, they are a bit annoying, but at the moment, due to the setup here, I can't get away from them. But you see here, this peak here at exactly 1 kilohertz, so 20 times the 50 Hertz line frequency, is at minus 62 dBs, and it could, if it couples into our circuit, it could disturb our measurement a little bit, because if it's superimposed on the 1 kilohertz line, then this gives a little extra noise here. Anyway, now let's go to the output of the first op-amp, which is simply a unity gain buffer, and we expect no additional harmonics anymore, and you see there aren't, at least to the minus 100 dB level. Now let's go to the op-amp where we suspect we get some extra noise. That is the second op-amp, which has a gain of 7.9, and here they are. Here are the, and you can see, because they are not exactly centered on 2, 3, etc. kilohertz, they are exact multiples of our not exactly 1 kilohertz tone. It's lying around 900 185 or something like that. And you can see the largest peak is at around slightly below minus 80 dB. And if you would add them all up, this is not the optimum. Well, minus 80 dB is just 0.001%. So this is barely below what we need, but it would be better if we would have these harmonics here at minus 90 dB at maximum. So just not to give an extra, so that in the end we don't measure the harmonic distortion of our amplifier that we want to measure, but in the end we get a little extra distortion just from the OpAmp. So now is the time to search for a better OpAmp. And well, you could talk hours and hours about searching the right OpAmp, but when you have done this a few times, you will have a handful of favorites. And one of the nearly drop-in replacements for the NE5534 is the former Burr-Brown, now TI OPA or OPA, don't know how you want to call it, X134 series. And you can already see by the last two numbers, 3-4, that these were designed just to be a better replacement for the NE5534 series and its companions or cousins or brothers. And let's take a look at the first page. Superior sound quality, ultra low distortion. This is quad 08%, so this is more than 10 times better than the NE5534. So this already qualifies as the right OpAmp for us. But of course you have to look at all other specs. So it says low noise, but at 8 nanovolts per square root of hertz. And we had the NE5534 at, let's go back, at, where is it? The better type, the A type, has only 3.5. So concerning noise, it's around a factor of 2 worse, but we have seen we have such a large margin in the noise of the OpAmp that this is no problem for us. What later will be of interest, it has true FET inputs with very low bias currents of 5 picoamps. Let's compare this with the bipolar type. Here, look what we have here. We have bias currents of typical 500 nanoamps. So this is 100,000 times worse, depending on if it's really important for us. But we will talk about bias and offset currents and the offset voltage already here at 0.5 millivolts typical. Let's compare this. If this is of any interest, here is another case. We will see this one has around 1 millivolt offset voltage. Slew rate and bandwidth are nearly equal to the NE5534, but we have a high open loop gain of 120 dB if we put it in a 600 ohm load. We have a wide supply voltage range. You get this in single, dual and quad version. That's what the X is standing for. The OPA134 is the single one, the 2134 is the dual type, and the 4134 is the quad type. This looks in nearly all the specs better, and the specs that are slightly worse, like the noise and the input offset voltage, they are of no importance to us at the moment. But the ultra low bias current here could be even of advantage in another stage of our total harmonic distortion meter. So at first look, this seems to be absolutely superior and the right replacement part to get away with our distortion at the second op-amp. But let's take a closer look. So if we scroll down, we see an interesting graph here. Here we see that the distortion at an output at nearly full swing, 10 volts RMS into a load of 2 kilo ohms, is slightly dependent on the supply voltage. The lowest value is with the highest possible supply voltage of plus minus 18 volts. Now we have only plus minus 12, but we are still 100% safe, on the safe side, because we are better than 0.3331%, even with a plus minus 12 volt supply. Now let's look a little bit further in the datasheet. So, and here we have an interesting graph. I'll enlarge it a little bit still for you. Here we can see the effect of gain. The ultra low total harmonic distortion is at a gain of +1, or a non-inverting op-amp with a gain of 1, just as in our very first input stage. But when we go to a gain of 10, then we have nearly 10 times worse value, scraping at the 0.1%. This is still sufficient for us, and we know we only have a gain of 7.9 or 8, so we will be slightly lower, and this still qualifies, and this is the right op-amp, at least one possible op-amp. The other conditions here, you still have two different graphs for different loads, 2 kilo ohms and 600 ohms. Now we have loads that are higher than that. The highest load here I can see is 10 kilo ohms, so this will be no problem. Output voltage of 3 volt RMS, we're even lower, so we have absolutely no problem with our supply voltage, with our load, with our output voltage. So we will certainly be below 0.001% at our second op-amp stage, which is the critical one. So let's simply try this out. Exchange our second op-amp with an OPA134 and see if we get rid of our harmonics generated from the slightly worse op-amp, the NE5534. And let's see. I have to take out the right one, of course. Let's see if this improves our slight distortion problem. And here we are. No distortion at all, just by using a better op-amp. So this is quite nice. We got away with any extra distortion from our op-amp just by using a better one. So we got rid of our op-amp induced distortions here with replacing it with a better one. But still, we already mentioned this. Is this really such a good idea? We have first of all a resistor divider as an input attenuator. Then we have a buffer. Then we have another resistor attenuator, a variable one. An amplifier. Then again an attenuator, this time not in the shape of a resistor divider, but by an inverting op-amp with a smaller than 1 amplification, so couldn't we improve on that, making it all possible with 1 or at maximum 2 op-amps instead of 3? And this will be a topic of either the next or the second next episode. So anyway, next episode we will try to redesign this 3 op-amp input stage, and we will talk about DC errors like DC offset and input bias and input offset currents. Although we know that in our meter here we are only measuring AC signals, but you still, even in an AC measuring device, you have to take care of DC errors, and we will see in the next episode why and how this can affect our accuracy here. So that was it for today. Thanks for watching. Until next time, bye from Roger, bye from Labs.